Hello everyone, my name is kasra EdalatNejad, and today I'm presenting Janus, safe biometric deduplication for humanitarian aid distribution. This project is a collaboration between EPFL, International Committee of Red Cross, or ICRC for short, and CISPA. Humanitarian organizations offer help to people in need. This process often starts with people coming to a registration desk and asking for help. Then ICRC will assess their need, and if they are eligible, they will assign monthly aid packages to them. The problem arises if intentionally or by mistake recipients repeat this process multiple times and get multiple packets of aid. Humanitarian organizations often have very limited resources and budget, and they try to be as strategic as possible when allocating them. If recipients can register multiple times and receive multiple packets, then this organization cannot help as many people as they want. This problem is called deduplication, where a registration session needs to determine if a potential recipient is a new user or somebody who has registered before. There are different approaches to handle this challenge. One common sample is using phone numbers, the same way that WhatsApp or Facebook do. But in some areas, it's very easy to buy multiple SIM cards. While if your target audience live in the middle of Sahara, a large portion of them may not have access to phone numbers. So this option does not give us the functionality that we need. An alternative is relying on government ID. But Red Cross often operates in conflict zones where users are escaping for their life, and keeping their ID safe is not their top priority. And beyond this, there are areas that Red Cross operate that there is no government to issue these IDs at the first place. So these government ID do not give us the functionality either. Another alternative is biometric. Fortunately, we have a higher universality there, and most recipients have their hands and face intact, and we can use this for deduplication. And the functionality there is rather straightforward. The registration station just needs to add a biometric sensor at the desk, and whenever a recipient tries to register, take a biometric sample from them and store it in a biometric database. If they try to register again, when taking a new biometric sample, we can detect that we already have this user in our database. However, this creates a biometric database of a very sensitive population that can put both the Red Cross and their aid recipients at risk. That's when Red Cross came to us with this question, that is it possible to use biometric to prevent double registration without creating risk for the Red Cross or their recipients? We investigated the requirements of performing deduplication in humanitarian aid distribution, and I'm going to present a subset of them here. First, on the functionality, we need to be able to perform deduplication to compute a binary membership status P that determines if a recipient is a new user. Then we need to ensure a low failure rate. If by mistake our system decides that the new person in need is a duplicate and prevent them from accessing the aid that they receive, this would have a very high human cost. Then on the safety side, we need to ensure that our system has a single functionality and purpose, meaning that no information beyond the binary membership status P will be revealed. This includes, but is not limited to, preventing access to raw biometric material, biometric templates, or being able to repurpose the system to perform biometric authentication and identification. Moreover, we need to ensure that we provide protection against passive and active compromises. We want to ensure that a single actor in our system will not be able to learn any information beyond the output that it should learn. And we want to ensure that any query will only the output with collaboration with the organization itself to prevent cases such as Taliban taking control over Afghanistan and getting control over biometric devices, allow adversaries to have access to our membership queries without collaboration from the organization. And finally, we want to ensure scalability up to 10,000 users for our system. Now let's switch gears and talk about designing Janus. As we want to provide protection against passive compromises, we want to ensure that no single point of privacy failure exists in our system. And to do this, we need to distribute the trust between at least two active parties. We already have one active party in our system, the registration station, that interacts with recipients and can take biometric samples from them. We introduce a new party that we call biometric provider. And in the paper, we argue why the immunities and the structure of Red Cross allows it to independently and securely deploy this party in the headquarters or delegations of Red Cross. And we assume that both parties are honest but curious. Let me give you a workflow of how deduplication works with Janus. First, a recipient comes and requests to be registered at the registration station. This leads to performing a membership request from Janus that takes a biometric sample from the user and interacts with the biometric provider counterpart of Janus. This results in a binary membership status that is revealed to a human at the registration session that makes the final decision. If this decision is positive, both Janus compartments interact together to add this member to existing user database. And regardless of the outcome, all plain text and raw biometric material will be deleted from the registration session at this step. And we will finally inform the recipient of the decision. To move further, I'm going to give you a simplified view of how biometric works. Biometric sensors take images from biometric modes such as fingerprint or irises, and then these images are processed into templates. Templates are fixed size arrays of integers. As this process is probabilistic, if you repeat it multiple times, you will get different templates. So equality between two templates will not work. That's why we have a procedure called biometric matching that takes two templates, X and Y, and determines if they are taken from the same user. To do this, we compute the distance of two templates using metrics such as Euclidean or Hamming distance and compare it against a threshold. We designed 3 different instantiations of Janus based on different technologies to get different trade-offs. First, we have SMC Janus that relies on secure multi-party computation. Second, we have hybrid Janus that combines homomorphic encryption with secure multi-party computation. And finally, we have T-Janus that relies on trusted hardware. During this time, I'm going to solely focus on the hybrid version of our protocol and fully omit SMC Janus and T-Janus. Homomorphic encryption, like most other encryption, starts with a key generation that creates a secret key and a public key. And we have that generic encryption and decryption procedures, and we rely on double bracket notation to show encrypted material. The interesting part of homomorphic encryption that it is possible to perform arithmetic operations such as addition and multiple depth of multiplication on encrypted values without any need to decrypt them first. And I want to highlight here that all these arithmetic operations and decryption is performed modulus a prime number cube. Now let's go through the design of hybrid Janus together. First, we have a setup phase where the registration session sets up the sensor and creates an empty database for storing encrypted templates. Then biometric provider generates a homomorphic encryption key and sends the public material to the registration session. During this talk, I'm going to use purple to show the registration session operation and green to show the biometric provider operations. Then we have the add member procedure, where the registration session takes a new biometric sample from a user, encrypts it, and stores it in its encrypted template database. Then we have the membership procedure that performs the duplication for us. In hybrid Janus, this process consists of three main steps. First, the registration session takes a biometric sample from the user and loads encrypted templates from its database. Then we use the homomorphic properties of our encryption to compute the distance over encrypted material. For Euclidean distance, we first performed the square of pairwise differences and sum them up together. The registration session repeats this process for all n users in its database to compute n encrypted distances. However, performing the comparison and threshold with homomorphic encryption is very costly. And sending these distances directly to biometric provider to get decrypted reveals distance, which is a sensitive information. So to handle this, we'll rely on secret sharing, where registration session chooses random values in ZQ and deduct them from the distance and send them to biometric provider to get decrypted. As I highlighted before, all arithmetic operations in our encryption scheme are performed under modulus Q. And this ensures that these two sets of value are arithmetic secret shares of distance under mod ZQ. Next, we rely on a garbled circuit to reconstruct the secret shares that we have to get distance. We compare the distance against the threshold to determine the matching status of every template in our database. And we combine these matching statuses together to compute a database-wise binary membership status and reveal it only to the registration session. Now let's switch gear a bit and talk about the practical aspect of biometric. Janus provides support for all three major modes of biometric, namely fingerprint, iris, and face recognition. One of the most important aspects of biometric are their error rate. Anyone who has used biometric on their phone already knows that sometimes they make mistakes. And in here, we are going to expand them a bit more. We are going to use a naming notation for biometric identification here. And we use false reject rate to show cases where Janus fails to detect a duplicate request and a recipient double registers, which is unwanted. Then we use false accept rate to determine cases where Janus refuses a new eligible recipient and refuses to provide help to them because of a biometric error. In our system, this has a rather high human cost, which is way more important than our false reject rate. We first assess the matching error, and as our computation closely follows what happened in plaintext biometric, we have the same error rate as plaintext matching operation, which is out of a scope of our study. And the sensors often have a false positive rate between 0.01 and 5%. Our membership builds on top of the biometric matching operation. And performing membership leads to having n matching operations when going against a database of n users. While the error rate of a single matching operation is good enough for an authentication, when we plot the probability of failing to register eligible users as the size of database grows, we see that for the case of 10,000, we will almost always fail. But we know that they are big biometric systems. For example, we have Aadhaar, India's national biometric ID that supports identification of more than 1 billion users. And identification is very close to deduplication. So how they do this? Well, it's rather simple. Every human have 10 fingers, 2 irises, and 1 face. And if you combine all of this biometric material together, you get a way better error rate. This process is called biometric fusion, when F biometric samples are fused together. This can be single modal, like using 4 fingers, or 2 irises, or it can be multimodal, like combining fingers and irises together. And we have the 2 fused templates match together if all their underlying F samples match. Now, after biometric fusion, we redo the plot that we have, but instead of having a simple sample per user, we allow up to 4 samples. And we see for 2 cases that we have 4 fingers or 2 irises with common biometric sensor errors, we can achieve an acceptable error rate even when we have 10,000 users. To the best of our knowledge, we are the first privacy-preserving deduplication system that can achieve error rates that scales beyond 10,000 users. And if the Red Cross want to reduce these error rates further, the process is as simple as adding more samples per user. We implemented all 3 instances of Janus. We use EMP framework to handle our SMC-based operations in C++. We use the Latigo library to perform homomorphic encryption operations in Go. And finally, we rely on photonics to perform operations in an SGX enclave in Rust. In here, I'm showing you the evaluation of hybrid Janus when we are considering 1 or 4 fingers or 1 or 2 irises. And the important part in here is that computing membership with hybrid Janus over a database of 8,000 users with 4 fingers that gives us an acceptable error rate is still practical. And we just need to have 4 seconds of computation and 150 megabytes of transfer. In the paper, we compare our costs to prior academic work and showed that we improve upon them. In conclusion, we studied the requirements of biometric deduplication for preventing double registration in humanitarian aid distribution. We proposed Janus, a privacy-preserving deduplication system. We designed 3 instantiations of Janus based on secure multi-party computation, somewhat homomorphic encryption, and trusted enclaves. We are the first biometric privacy-preserving deduplication at a scale, and we have a versatile design that supports 3 biometric sources, in addition to biometric alignment and fusion. Thanks for listening to my talk.